This is Amy St. Croix with the Statistics Division. Our speakers today are Dr. Connie Borror and Christine Anderson-Cook, both of whom are fellows of ASA and ASQ, and are regular contributors to the Statistics Roundtable column in the Quality Progress magazine. Connie earned her PhD in Industrial Engineering in 1998 from Arizona State University. She's also former editor of the Quality Engineering Journal and is currently a professor in the School of Mathematical and Natural Sciences at Arizona State University West. And Christine is a research scientist in the Statistical Sciences Group at Los Alamos National Laboratory. And she also served as the 2010-2011 chair of the Statistics Division. So today, Connie and Christine will be presenting on the what's and whys of different kinds of data. This was a popular talk given at the 2013 Fall Technical Conference in San Antonio, and we're now happy to share it with the division via webinar. All phones and microphones have been muted except for those of the presenters. So if anyone has any comments or questions during the webinar, please use the questions interface and go to meeting. I will relay those questions to Christine and Connie at designated times during the presentation. So without further ado, I am going to hand things over to you, Connie and Christine. And thank you again for presenting with us today.
Thank you. This is Connie Borror, and thank you, Amy, and welcome everyone. Christine and I are very excited about giving this talk. We've enjoyed putting the paper together and presenting at the Fall Technical Conference. And what we want to do today is talk about the what's and whys of different kinds of data. This is an introductory level talk, and our goal is really to discuss how and why we collect data and start to connect any overall strategy like the DMAIC process, statistical engineering, what have you, for problem solving, connecting that to how do you collect data. So during this presentation, sorry, it wasn't letting me move that. Sorry. What we want to do is talk about the different tools for data collection, just provide you an overview of some specific tools, some connections to statistical engineering and the DMAIC process. And one thing about this talk is, and the paper, is we purposely made it tool-focused versus problem-focused. And the reason is that, understanding the tools and what tools are available and what they do is very important before we go jumping into how do I solve a problem. Think of it as, if you're going to build some furniture or maybe a tree house, you can't just jump in and grab the toolkit and hope to build something right away. You really want to understand what tools are available and how to use them correctly, and then you can focus on the process of building something. It's kind of like, we need to walk before we can run and know what options are available to us. So we're going to talk about 7 different tools, give you an overview, how data are obtained, what to do with the data, some common misconceptions and mistakes. And at the end, we'll end with an example that kind of puts all the pieces together. It is a coherent piece. So let's get started. This was a table that appeared in our article, and it summarizes the different seven different data collection strategies, which are observational studies, monitoring techniques, process capability, measurement assessment, sampling, design experiments, and what we termed complementary data and information. And as you can see, these collection strategies range from, in observational studies, using conveniently available data but it's difficult to establish causal connection, all the way to, in designed experiments, actively manipulating factors to establish causality. And we also thought it was really important to talk about this complementary information and data where you've got some qualitative data where you've been brainstorming, you have expert opinion, and some informal assessment. And you can see that some of the common techniques that are used for each of these strategies, data mining, contingency tables, convenience sample regression for observational studies, SPC and control charts for monitoring techniques, gauge R&R studies for measurement systems analysis, just some examples, and maybe response surface confirmatory studies for designed experiments. And so what we want to do is, I'm going to turn it over to Christine now, who's going to talk about the DMAIC process, observational studies, sampling, and a little bit more on designed experiments and how they relate to these data collection activities. So Christine, I'm going to turn it over to you.
All right, thank you. So we're just switching screens here, and hopefully everyone can see that we're now looking at the slide that talks about the DMAIC process. So again, we're going to focus mostly on tools, and I think it's helpful to be reminded that each of these tools could be themselves a one-hour webinar to talk about them. So we're just going to hit sort of high-level details or high-level view of these, but we're going to try to connect it to where we might see it in a structured problem-solving approach like the DMAIC process. So to start that, I'll just sort of recap what the focus is of each of these 5 steps, and on the screen you can see where the 7 different data types that we're going to be talking about show up as a primary consideration. And it's important to remember that any of the data types could show up in any of the stages, but these are the most common ones that we might see. So remember that the define phase is all about making precise what we're trying to solve. So taking a sort of fuzzy problem and turning it into something crisp and concrete. And so we want to use observational studies and complementary information as a way of sort of making that problem statement more precise. The second stage is the measurement stage, and the key part of that is that we want to be focused on making sure our data are high enough quality that we can trust what we're seeing. And there's a specialized set of data collection tools in measurement analysis, measurement assessment, that really is focused on just that problem. In the analysis phase, we're looking at an assessment of where we are now. So sampling and monitoring techniques and process capability can help show us where we are. And we'd also like to get started with identifying promising potential solutions, and so that may involve a little bit of designed experiment. The heart of the process is the improvement phase, where we're actually manipulating the system and trying to understand what combinations of our inputs could lead to improvement, and so a designed experiment is quite natural there. And then lastly, in the control phase, we're trying to capture those gains and build them into a new standard operating procedure, and so monitoring techniques and process capability figure prominently in that. So one very important aspect of these different data collection strategies is the degree of control that we have during the data collection process. And so Roger Hurl and Ron Snee have been talking quite a bit recently about data pedigree, that if we understand where our data came from, then we're going to be able to make better decisions about how to use that. And so this is very much in that spirit. And so if we think about degrees of control, the data that has the least control associated with it obviously is observational data. And where this becomes important is the kinds of conclusions that we might want to draw from that should be the weakest. In other words, we don't want to just look at an observational study and then make a decision about how to change our process. We want to use that for information to help our understanding, but we want to do something much more control-oriented, or where we've in fact designated how the data were connected before we actually step in and change our process. In the middle range of least and most control is sampling, where we have a collection of units and we're going to draw a subsample or a portion of that population from that. And because we have the control of which units to select, that allows us to draw stronger conclusions in that the sample, if we do our sampling correctly, will tell us something quite specific about what the population characteristics look like. And then the most control is the designed experiment category, where we're actively manipulating those inputs, and then as a result of that, we're able to observe things. And so in this case, we're able to establish causality, and that's a much stronger set of conclusions that we have. And so that's sort of the three big categories, and then our other 4 data collection strategies all are interrelated to that. So measurement assessment is really a specialized set of designed experiments and so on. So what's important here is the degree of control. What's connected to that often is cost. So having less control with an observational study, quite often that data is cheaper to collect than a designed experiment where we are much more involved in manipulating things, and so that makes it more expensive. But then also we should remember that that translates into how much we should trust the results that we have and what kinds of conclusions we might want to draw from that. So now let's jump in and actually talk about the different kinds of data. So the first one is observational studies, and this is a very important category mostly because it's so common in many different applications. So we're going to encounter this kind of data almost certainly, and so it can be very helpful for building background and providing insight. But I think where we want to be careful, as we see it throughout the DMAIC process, is that because there's no active manipulation, we should be very cautious about how we draw conclusions with it. And making decisions just based on seeing results in observational studies can in fact lead us astray. So how can we get into trouble with observational data? Well, if the pattern that we're observing comes from a convenience sample, there's no guarantee that, in fact, that pattern will be present in the larger population. So if we look at data from the start of a production process and then make the assumption then that same pattern carries on for the mature process, we might be surprised that, in fact, patterns change or our particular subset of data doesn't, in fact, represent what we're seeing in the larger population that's really of interest. The second one, quite often instead of thinking about association between the inputs and the responses, we want to take that stronger step and assume that causation is involved, and that can lead to all sorts of trouble. So one example might be that the outputs, what we're calling the response, is actually driving the inputs. And so there we've got the causation relationship exactly backwards. Or point 3, we may have some lurking variable that we didn't measure at all, and that's actually the thing that's the mechanism for driving the change in both the inputs and the response. So just an example of that is we might observe that we have a higher defect rate in one of our processes, and that's associated with the night shift. And so it would be easy to assume that, in fact, that it's the fact that these products are being manufactured in the night shift that's causing the problem, when in fact the lurking variable or the driver of things is actually that people choose which shift that they work on based on seniority, and so we have less experienced workers working at night, and that actually is the driver of why we have a higher defect rate. So there we're assigning the wrong explanation to what we're seeing just because we have, what we measured may not be the complete story. And then lastly, we may just be looking at a subset of the data, but that subset isn't representative of the overall population that we're interested in. And so, we're looking at the wrong segment of customers or the wrong production line to get the overall characterization. So one very important exception to our caution about observational data is if, in fact, we're observing the whole population. Where we get into trouble with observational data most often is that we have a small collection of data and we're trying to extrapolate to generalize about the whole population. And if we have the whole population, any pattern that we see is actually there. And so I think that actually changes the rules. Where we can get into trouble is that we often have a tremendous amount of data available, and so this gets us into statistical techniques like data mining or analytics, which are becoming very popular as it gets easier to automate data collection. And so here we really have to be very careful to focus on what is the goal or what are we trying to extract from the data, because we can identify a whole bunch of patterns, but if they're not helping us to focus on the problem at hand, then that may not be as beneficial as we would hope. So what are some of the key considerations here? Number one, I think we want to make sure that we have the relevance of the data that we have in hand to our current study. A lot of times observational data comes because we've inherited it from some previous source, and so it's important to think about, has anything important changed in the process since the data were collected? Was the focus and therefore the population that the data were drawn from, is that different between the two studies? Data quality is also very important, understanding just how good the data are and how much we should trust them. That's an important consideration. And then making that connection between the data that we have and our particular focus is a very important piece. And we want to be cautious about drawing those conclusions and thinking about causality, because that really should be off the table for an observational study. So that was the first of the data types. Now we're going to transition to something where we have a little more control, and that's the sampling scenario. And so here the primary driver of this is that we're looking at a fraction of the population with the goal of being more cost effective. So cost here can be measured either in dollars or in time savings. But a lot of times if we do sampling correctly, we can get a high quality answer that's much more cost-effective than looking at the entire population. Another major category where sampling becomes very important is if our testing involves destroying the item that's being tested. So I do some work on military applications, modeling the reliability of different missiles, and to get a good assessment of reliability, the best way is to actually fire off that missile. And so that's a very expensive test, because not only is it expensive to do the test, but also you're depleting the supply of items that you have available for when they're needed. So the key idea is we can get an accurate and a precise estimate of the population if we're careful about how that sampling is done. So a couple of key considerations to think about as you're designing a sampling data collection strategy. So first, we need to be very clear about what we're trying to accomplish. And so a lot of times that comes in the packaging of defining the population frame. So are we interested in understanding characteristics of all of our customers or just the customers that have complained? Both of those could be very sensible questions to ask, but they're very different questions. And so what pool of people we're drawing from will have a big impact on what our results generalize to. The focus of everything is to come up with a representative sample, so one where the characteristics of the sample match as closely as possible the overall population. And so we'll have to think about things like the sampling units. Imagine a telephone survey. We may be interested in looking for individuals, or we may be looking at households. In a production environment, we may want to sample individual units, or we want to maybe make the sampling unit a lot of units, or an hourly increment that we're sampling from. And then, of course, we have to think about how many units do we need to look at and measure to be able to have sufficient precision to draw the conclusions that we want. Another strategy that can improve sort of our confidence in interpreting results and also give us a higher quality answer is to use supplementary information, where if we're doing a political poll perhaps, it's helpful to collect gender and age information, and then we know what the characteristics are of the overall population on gender and age, and so we can compare those to see whether our sample matches up in a similar way to the characteristics of that whole population. The last big category of things that we talk about with sampling has to do with non-response or missing observations. So a lot of times we just can't collect data on every item that we want to collect on. And so we're looking, are there systematic differences about why some parts are excluded or why some people are excluded from answering? So imagine a scenario where the items that I can't get a measurement from are all excluded because they're too big to fit into the measuring device. There I would have a very systematic mechanism for eliminating some of those items, and so results from the observations that I get would not necessarily be representative of the entire population. So just briefly, some cartoon versions of the different kinds of sampling that are commonly used. So picture a big jar full of marbles. In simple random sampling, what we're going to do is just pull out some of the items from that population where each of the items has the same probability of being selected. So here we're just picking 10 of the 100 items or so on, and this is the most simple way that we can do a sampling strategy. One notch more complicated than that is to look at stratified sampling. So here I've taken my marbles and I've divided them based on size and shape into 3 different categories. And then I'm going to draw a sample from each of the categories where the proportion that I draw from each of the strata is proportional to how many units there are in that strata relative to the whole population. So this allows me a bit more control to make sure that I have enough big ones and enough medium-sized ones in my sample because I've strategically chosen those to match the proportions in the actual population. Another kind is cluster sampling. So here there's a natural grouping. So imagine these are boxes of parts. And so here I'm just going to choose a certain number of boxes. Here are 5 boxes, the red ones. And every item in that box is then going to be measured. So that's cluster sampling. Multi-stage sampling is closely related to that, where we start off with these groups of units, here groups of size 8. I'm going to pick a few of those groups, and then instead of measuring every unit within that, I'm going to just choose a sample from within that grouping. So here 3 items are drawn from that collection of 8. So it's just the sampling is done in 2 stages. The last major category of sampling is systematic sampling. This one is by far the easiest to automate, where we're just going to measure every 5th unit that comes off of a production line. And the key thing here is to make sure that we're not matching up with any natural frequency that we have in our process. So imagine that we had 5 production lines and we merged together all their output. If every 5th unit comes from the first production line, then this sampling strategy would actually get us into quite a bit of trouble potentially, because we're never looking at any of the other production lines. So that's 2 of the categories. The third one is designed experiments, and again we've moved from observational to sampling to designed experiments. We're bumping up the degree of control that we have. So generally this will be the most expensive data collection type, but also allows the strongest conclusions. So one aspect that often gets overlooked in designed experiments and leads to a common problem is that experimentation most often is very sequential in nature. So we don't just jump in and do a single shot experiment, but we want to work through this progression in many situations to make sure that we're actually understanding our process in the right order. So a first step, a pilot study, looks at what kinds of inputs we might be interested in, and then what ranges make sense for each of those factors or inputs. And we want to make sure that we've got measurement issues out of the way and understand what kind of data could come out of that. The next step is a screening experiment where we understand which of those factors actually seem to be the big players in affecting the response. So quite often here we're going from a large number of factors down to a smaller number, where our criterion for eliminating factors is that they just don't seem to have much impact on the response. The third stage is a response surface stage where we're actually taking those remaining inputs or factors and looking at the relationship between them and the response or responses. And as the name implies, we're actually building a statistical model to characterize that relationship. And we want to, as a result of that response surface, we want to choose an optimal combination to get the ideal response that we're wanting. So we may want to maximize yield, so we would look for a combination of inputs that in fact optimizes that. And then we shouldn't trust our statistical model too completely. We'll probably want to do some confirmatory study where we look at that optimal combination of inputs and make sure that we actually get the kind of responses that we want. So matching up what kind of design we choose should in fact be based on the goals of the experiment and what's important. And this, I would say, is the biggest mistake that I encounter when people are using designed experiments, is a lot of times they'll choose a screening experiment when they're interested in characterizing the relationship, which should be a response surface type design. The three core principles of design of experiments, we've probably all heard these before. So randomization is all about removing systematic bias. So if my oven, unknown to me, gets warmer throughout the day, if I've randomized the treatment orders and how I collect the data, this offers some protection from that being completely confounded with something that's changing that I'm unaware of. Replication is all about calibrating what a big difference is. If I understand how related observations are, where I think I've done everything the same, that gives me some sense of the natural variability of the process. And so that helps me understand whether a difference that I've seen between the high and the low level of a factor, is that in fact big or not. And blocking is all about efficiency, where if I compare different treatments or different factor combinations in units that look more similar to each other, then I'm going to have better ability to detect small differences. And so this is, I'm going to divide all of my units into groupings that look quite similar and then assign my input combinations within those blocks. Okay, so when we're trying to decide on a good design, what are some of the considerations that we should be making? And so this is a list of 11 different metrics for what constitutes a good design. And I'll just talk about them in terms of some categories. So the first one is, I assume I've got the right model, everything goes wonderfully. So under those scenarios, I want to have good estimation and good prediction for my chosen model. The next category says my model has assumptions, so I'd like to in fact be able to see whether those assumptions are a good match for the data that I've collected. Then I want some protection if things go wrong. So if I set my input at 210 degrees instead of 200, I'd like my design to survive that. I also, with the sequential nature of experimentation, it would be nice if I could recycle data that I got from the screening phase and use it in the response surface phase. And then lastly, if I make my design bigger, that tends to make it better, but I'm going to have to balance the overall cost with some of my other considerations. Okay, and then lastly, just there's two major categories of design. So one is the classical design. These are the ones that you probably learned about in your introductory statistics class, where we specify the number of factors that we have, how big our overall experiment will be, and then we look up a table and can use that design for our scenario. So typical kinds of designs on the left-hand side, that's either a factorial or a fractional factorial design, very common in screening design applications. And then on the right-hand side, that's a central composite design. That would be a very traditional choice for using in a response surface setting. So these are, they have nice geometry, they look pretty when you plot them, and they have good balanced performance across multiple objectives. So that's sort of historically how things were done in the design of experiments world. And then the other category that's really just emerged in the last 10 or 15 years is a computer-generated design, which is much more flexible to the size that or the biggest size of design that I can come up with, any constraints, maybe some input combinations are not sensible, and I can tailor it to my objectives. So these are things in JUMP or in Design Expert that we might be able to generate specific to our particular case. And so these are sort of the two categories that we might consider. So I'm going to pause and take a breath and transfer things over to Connie. And I think we might see if there's any questions at this point that would be good to respond to. So.
Okay. If anyone has any questions for Connie and Christine at this time, you can just type those in the questions interface. I haven't seen any so far relating to the material on the slides. Give just a minute here. Okay. We'll proceed with the presentation, and then if questions come in, then at the next transition period, we'll go ahead and discuss those. So Connie, you can go ahead and take over.
Okay, thank you. And thank you, Christine. Now let's switch gears a little bit and talk about some more data collection activities and collecting data for monitoring purposes. Say we have a process in place and we want to know, is our process stable? Do we have process stability? Is our process in control? And in these types of techniques, we know that variability exists in all of our processes. We don't get the same value or the same number each time we collect data. We don't get the same average. It's changing. We have variability. So we want to monitor that. What's our natural variability? We like to use, for example, some of the best tools for monitoring a process are control charts. And we want to be able to look for, in our variability, do we have some problems? Is our process out of control? And is that caused by something that's just naturally occurring, or is it something that we can assign or say that we have an assignable cause for that, that outcome? And so control charts can be very useful for monitoring processes and trying to identify process stability. And very commonly used in the analyze and the control phases, and for two somewhat different purposes. In the analyze phase, we can use control charts for initial assessment. Maybe we have a process and we haven't really been monitoring it with control charts, but we want to start doing that. Or we have a new process and we want to start monitoring it to see where are we at now? What is our current as is? Is our process in or out of control? We're looking at the natural variability of the process and comparing that to these control limits, or the upper and lower control limits on a control chart. So we're looking for this idea of process stability. So control charts, which I want to expand on a little bit, are key tools for the monitoring process and collecting data so we can see if the process is in control, i.e. the process being stable. So one of the things that I often want to do here is, before using a control chart, I want to ask yourself a few questions. I always kind of start on the left-hand side, and these two things that you see on the left-hand side, what are you measuring? And is the process currently unstable, out of control? Oftentimes those two things go together. If our process is out of control, it may, if we know that it's out of control, we might have been notified by our customer, or maybe our customer says that our product doesn't seem to be meeting their requirements and they're asking us what's the problem. And we want to know, all right, is our process currently unstable? Is it out of control? And someone maybe, you know, one of the first things, if they come to me and ask for help, if they're working on the process, they'd say, you know, I'll be asking them, well, what are you measuring? You know, what is it that you want to measure? What is our design here? And, you know, let's say, for example, that they make parts and an important characteristic is diameter. So they'll tell me, well, diameter of this part is what we're measuring. And then my next question would be, well, what are you going to monitor? And then they look at me kind of funny, and then they say, well, diameter of a part. And so I kind of push back a little bit and say, no, I understand that's what you're measuring, but what is it you really are going to monitor? That's a different question. So for example, you may be measuring the diameter of the part, but what are you going to be, since you know you want to do a control chart and you want to start doing that, well, what is it you're going to be plotting? So for example, if it's diameter, are you going to take individual parts, measure the diameter, and plot the individual measurement on the chart? Is that what you're going to monitor? Or are you going to take a subgroup of parts, say 5 at a time, measure all of them, get the average, and plot that on the control chart and monitor the average? Or another thing is, what if you take the measurement of this group of part, you might take 20 at a time, take each diameter, and all you want to do is say whether or not the diameter you took, the measurement you got, falls within a range or not. So you're just interested in the number that conform or the number that do not conform out of the 20. That's a proportion. That's a different chart that we have to use. So it's a difference between just what are you measuring, but what are you also going to monitor? What's the important characteristic that really tells you if your product is good and is what is stable and the process is stable? And of course you have to know what type of data does that follow. Is it discrete? Is it continuous? Is it categorical? To help us identify what kind of control chart I should be using. And then the next thing I often ask is, well, let's step back even more. Is there more than one quality characteristic that you want to monitor simultaneously? Let's say, for example, this part we're monitoring actually looks is a washer. Looks kind of like a donut. So we have an inner diameter and an outer diameter. And you want to monitor both of those. Do you think that there's a correlation or relationship between inner and outer diameter? Possible. So anytime that you're monitoring more than one quality characteristic, what you have to ask yourself or think about is there some type of correlation going on between those two quality characteristics? Should I be monitoring each quality characteristic separately, like in the top two charts are a chart for, say, variable x, which might be inner diameter, and on the right-hand side at the top is the outer diameter, and I'm monitoring them separately using two univariate control charts. And if you look at those two charts, you say, well, it doesn't seem to be any problem, doesn't seem to be anything control. I see differences here. See a little drop in the later observations for my outer diameter on the right-hand side up there. But nothing really is jumping out at me. But if there's a correlation between these two, we probably should be using the type of chart that you see at the bottom of your screen, which is a multivariate control chart. A multivariate control chart, that bottom chart that you're looking at there, folks, is using the exact same data that is in the two separate charts at the top, except now we're taking into account a possible correlation structure. And if you notice, we have a point that is plotted out of control, which wasn't identified per se in the top two, even though there might have been something hinting at it on the right-hand graph at the top. But what you're seeing there is now we've got this out of control point. We need to investigate. Was that just a false alarm? Or was there something truly that's going on there that's going to make that an out of control process? So we need to look at that. So if you have more than one quality characteristic, you want to use something that might take into account the correlations. And you can do this for many quality characteristics at the same time. The drawback of multivariate control charts is being able to identify the culprits behind out of control points. And that's one reason for their drawbacks is trying to identify, well, if it was the x variable or the y variable, which one is it and how am I going to know? Individually, you might be able to find out, but when you add a lot of these together to do them simultaneously, it can get very cumbersome. Now next, we just talked about process stability and using control charts as a tool to monitor a process and collecting data, which we'll talk a little bit more, and the data that's collected for building a control chart to look for process stability. But what about process capability? Okay, let's say that my process is stable, but is it capable? That is a different question. Process capability has to do with comparing the process variation, the natural variation in this process, to specification limits or outside requirements, maybe by our customer. So on the left-hand side, we're looking at process stability. comparing our process variation to control limits, the natural variability of the process. Right-hand side, if I plot that same data and maybe it falls and follows a bell curve that you see in front of you, those are all of my diameters, for example, nice bell curve, and the tails are not going beyond, don't look like they're going beyond the spec limit, so I'm probably making very few parts that are out of spec. That's a good thing. But imagine this. Imagine the variation increases in this process so that my bell curve gets fatter and wider. What's going to happen with the tails? They're going to start going over our spec limits. I'm going to start making a lot more product that's out of proportion or outside the spec limits. Another thing is my variation doesn't change, but my system goes off target. My process is off target. Maybe my normal curve has shifted left or right. So I've gone over one or the other spec limits. Again, a lot more proportion non-conforming. How can I be able to assess that? Well, people like to assess capability using some indices. Some of the metrics that are used are capability indices, such as C sub pk, often referred to as kind of a short-term metric, and P sub pk, P sub p, more long-term variation measures. You could look at a stability index, which is the ratio of those two. And I put in a figure down at the bottom to kind of identify short versus long-term variation and what does that really mean for our process, for having an unstable and a stable process, and how that can affect the capability of our process as well. Now, the thing that is very important here as well is, single numbers are not the cure-all. And other things that we need to be aware of when we're looking at process capability and really stability for building a control chart are three things: time frame, sampling method, and finally your presentation of your results. The time frame of how you're collecting the data for process capability and stability should cover a period that allows for the process to be completely evaluated. It's process performance. We want to be able to, sometimes this is decided by our customers. They might want quarterly reports, monthly reports, weekly reports. Sampling method, how are you going to sample? This has to do with rational subgrouping. Are we going to, what's the size, frequency, or the number of subgroups that we're going to use, or that we might need to use? That all needs to be decided for your particular process. And finally, we think that presentation results are key here because people want to know, well, what's this telling me? Good things here are things like histograms, time series plots, but also if you're going to provide metrics, some of those capability metrics that I mentioned earlier, the C sub p, C sub pks, and so forth, try using some software, get the ability to put confidence intervals on those so that we can have a better estimate of those particular metrics instead of just a single value. Now we've talked about process capability, process stability. What about measurement systems? Process capability analysis tells us about the process, but what about the measurement system itself, the people that are taking measurements, the measuring devices, how the devices are set up? Is our measurement system stable and capable? Again, as we know, there's variability in all observed responses, all of that measurements we take. The variability could be due to the process, as we just talked about. It could be due to the measurement system, who's taking the measurements, how they're taken, and what devices, and just error itself. And the key thing here about measurement system analysis and assessment is, unfortunately, although people would like to believe it, some people like to believe it, automation and calibration is not a cure-all. We still need to do an assessment of our measurement system. So some components of measurement systems you see here. The two big overall arching components are accuracy and precision. You've probably all seen those target diagrams where they show this is accurate but not precise, this is precise and accurate. Well, this idea of accuracy and precision has to do with bias and then also our variation in terms of repeatability and reproducibility. So when we're assessing accuracy, we're looking at bias at a single point in time, bias over the entire range of different parts or objects that we have, and also bias over time. That's stability. Then we have precision, which gives us our measures of repeatability and reproducibility, where our gauge R&R studies come in. And here you just see some diagrams for bias, linearity, and stability, the accuracy for our particular measurement system. You can see poor linearity in the top frame. What we're plotting there is a measured value against the true value. What should happen if everything's in a nice perfect world is you should have that black line. You have zero bias, perfect linearity if our measured values are equal to the true value, if we know it. Then we could have poor linearity. You see that green line is not parallel to my black line. We have perfect linearity in the red line, but the bias is not zero, but it is constant. So nice tools to assess these types of things, bias and linearity, and stability are scatter plots, hypothesis testing, confidence intervals, and so forth. At the bottom, I was showing stability. Stability is nothing more than looking at how the average of a sample compares, or average of your measurements compares to the true value over time. So don't be a little misled by this graph I have here. These are 3 different time periods. And what's happening, the reason this is unstable, is that you see that as we move through the time periods, our little faces are getting farther and farther away from the middle value, the target value, the true value. Okay, so we see that deterioration over time because they're moving away from center. Good tools for this are control charts. And then precision. This is where we use gauge R&R studies. We want to be able to have a really good estimates of variability. Common metrics are often signal noise ratio, PTR, the precision tolerance ratio, percent R&R. We also want to include misclassification rates and things like that. Key tools, analysis of variance, designed experiments, control charts. And the idea behind this type of assessment about your precision is if the measurement system variation is small compared to process variation, then our measurement system is considered capable. What's small? That's why we got to know what's the natural variability in the process if we want to make sure the variability in our measurement system is smaller than that. And I put this little diagram here, and this is different from the previous one. And you see where it's pointing now at those 3 little groups of faces, good, better, best. The reason that outside little group is best, because it's best in terms of precision. They're all clumped together. They're very precise. They're not very accurate, are they? Accuracy would be that they'd be in our target, those middle 4 values you see. But those 4 measurements on the outside are considered best in terms of precision because they're very closely together. Okay? Things to watch out for these common metrics, though. They can be misleading. The metrics, some of the guidelines are misleading. The less than 10%, greater than 30% have been found to be problematic. And you may want to be very careful when using those. And lastly, the complementary data and information we talked about before. Overall, what I want to say here is that you want to tackle voice of the customer. Now, I hope that's what we're doing throughout all of this. But we also want to tackle the voice of the customer in other ways, maybe using this general 7 quality tools, histograms, control charts, and so forth. We want to transfer our voice of the customer to deliverables and outcomes. How can we take what they're saying, or what we think they're saying, and make them into outcomes? And we have many different tools that can address that. So at this point, I'm going to stop, and I'm going to turn things back over to Christine. And I'm going to see if there are any questions at this time.
Okay, we do have several questions and comments that have been populating in the questions window here for me. But I do realize that we have about 12 minutes left. So let's try to get through the rest of the webinar here, and then at the end, if we have some time, we can address some of those questions. If we do happen to run a little short on time, maybe I can email those to you both, and we'll go from there.
That'd be great.
Yeah, we'd be happy to do that. So remarkably, we are actually in pretty good shape on time. So
good.
We're in the home stretch here. So we've talked about the 7 categories of tools, and so now we just want to bring it back full circle. Remember, we want to have a collection of tools. We want to know sort of their strengths and weaknesses and how to use them, but we want to be very problem-focused when we actually start to tackle problems. And so just at a very high level, we'll talk through what this might look like for a particular DMAIC problem-solving example, and how these different data types could show up as we move through the process. So imagine that our problem is that we have a process, a production process, and it has too much scrap. Well, what will each of these stages look like just at a very high level, and where might we expect different data types to come in? And so define is all about really understanding where we are and what our specific problem is that we're going to focus on. And so it makes sense to use complementary data or information or historical data that we have available that's observational to help us identify, are there different categories of the defects that we should be considering? What types of defects are most common? What do our customers think are most important? And so here we're not using the data to actually make decisions, but we're just getting a good background on things and to make sure that we're actually starting at the right place and we've synthesized the information that are available, and then that becomes a good launching point for us as we move forward and identify potential candidates for solutions and actually explore that. But we now have a well-defined problem because we have it in the context of what's important to our customers, and that's based on data as a starting point. In the measure phase, this is all about making sure that we can trust the data that are available, that they are actually consistent with what's happening in the real process. And so we want to focus on accuracy and precision, and a lot of that is the tools associated with measurement analyses, which are really just specialized forms of designed experiments a lot of times, where we're collecting data in a very strategic way to make sure that we understand where variability is coming from, and that we have a clear definition of scrap in this case. Do we have mechanisms to correctly classify the scrap? And in our process, do we have early detection points or late detection points for when that scrap can first be identified? So all of that is just understanding what kind of data we have and how reliable is it in terms of helping us answer our question. In the analyze phase, now we're trying to get a more precise statement of the current status. So having historical information gives us some calibration of where we are compared to where we were historically. The process capability and monitoring really gives us a baseline. So if we do manipulate our process in subsequent steps, we have a point of comparison to see how much we've improved things. And then we're also going to lean on our experts' knowledge of the process in the next part of Analyze, which is all about identifying potential solutions. And so that may involve some experimentation, but also just sort of pulling in all of the background knowledge that maybe is more qualitative rather than quantitative. And so we can continue on with the improve and control phases, but what you can see as we talk through this example just at a high level was that we are very focused on what do we need to do, what question are we trying to answer, as opposed to how can I find a way of using this particular tool. And so I'm reminded of a quote that says, if all you have is a hammer, then it's amazing how many things start to look like nails. And so hopefully this has been something that guides you in the direction of knowing some different choices of tools and their strengths and weaknesses, and then how we might use them in the most strategic way to solve a problem. So I'm going to pass it back to Connie just for a few conclusions, and then we'll open it up for questions.
Thank you, Christine. And what as Christine was saying, is we are talking about, throughout this whole presentation, our goal is, again, understanding what are different data collection and analysis strategies that exist, giving a framework on how do you proceed in solving practical problems. You get an idea of what tools are out there, and getting a mastery of those tools, I think it can lead to, more confident problem solving. And so that's why even though often people want to be problem focused and on problem solving in presentations and how we work towards things, we believe that it's very important to understand the tools. So the long-term goal is to be solution focused, not tool focused, but it's absolutely critical to understand what the tools are used for and which ones should be used in what situations, and that it's not always prescriptive that you can only use a control chart in the control phase, or you can only use a designed experiment in an improved phase. That these can be used in different locations. And so we hope that this has been something that's been useful and helpful to you. We have for you on this PDF, on the PDF for this, some references as well. And I thank you again for joining us today, and we'll open this up for questions if that's okay.
Okay, thank you so much, Connie and Christine. We have about 5 minutes left here, but if anyone needs to drop off, the webinar is being recorded and it will be available for later viewing. So please refer to youtube.com/ASQ Stats Division, and you can please share the webinar with your colleagues and coworkers and anyone you think might have an interest. So I'm just going to browse through some of these questions here. Looks like we got quite a few, probably about 20. So let's see.
Well, like you said, if we can't get to all of them, we'll email. Email would be great too if we can't get to all of them.
Sure. So someone has a question about slide 19. They're asking, what is the characteristic plotted in the third chart on slide 19?
Yes, the third chart is at the bottom. That is that was a Hoteling's t-squared control chart, and I had it in here as plotting the median versus the upper control limit. No particular reason. I tried something different there, but this is a Hoteling t-squared control chart, and it's plotting the combination, a certain combination of the two sets of data that are in the top charts.
Oh, thank you.
Mm-hmm.
Another question here, what percentage of classical designs versus computer-generated designs do you generally see today?
So I think that's a little bit hard to judge. So I think it used to be, so 10 years ago, almost exclusively people were using classical designs, and I think that was just a computer-generated design was a high-end feature. So I may be talking about the strengths and weaknesses of them. If you have a sort of a problem that fits nicely into a classical design, then I really like the robustness of how they have good balanced performance across multiple objectives, you know, the protecting against things going wrong, being able to look at assumptions, things like that. But a lot of times now computer-generated designs are very popular when we have very tight size restrictions. So the classical design for a particular problem may involve 16 runs, but maybe my budget says I just have 10 or 11 as my maximum size. And so then that becomes a big driver for using the computer-generated design. Or I know in that queue, one corner is just not possible to collect data, and so it allows you much greater control. So certainly the computer-generated designs are becoming much more popular. In terms of a percentage, it would just be a wild guess, but I would say probably less than half still, but a growing percentage. Connie, do you have thoughts on that?
No, I think that's about right. I think as the computer capabilities improve and increase as they have been, I think that will also increase. But I think we're always going to have a place for those classical designs. But I agree with you, Christine. We see it as we have seen other constraints that these classical designs just will not fit, and taking just parts of them or fractions of them just are not going to satisfy all the possible objectives that you have.
Yeah, each type definitely has pros and cons. It's hard to quantify a percentage, though.
Mm-hmm.
Yeah. So let's see. Oh, I'm sorry, what?
It may also be quite specific to engineering applications versus biological ones. So, but understanding the trade-offs between the two, what they do well and what they don't do well, I think that's quite helpful.
Yeah. Okay, so another question here is a Latin square design considered a classical design?
I would say yes, because
Yes.
it's certainly been around a long time, and it's good for a very specific kind of thing where we've got a very limited run size. We're trying to look at a smallish number of factors and use a very coordinated way of putting together those factor levels where we're making some quite strong assumptions that we don't have interactions between the different factors. So it has its place. It's been around for a long time. But again, knowing sort of what the strengths and weaknesses of a particular design are, that's quite critical to using it appropriately.
In many of these designs, including the Latin square design and other classical designs, are often now commonly used as kind of, I'll say, jump-off points for some more computer-generated designs as well. Well, they'll start with standard designs and then maybe use a genetic algorithm or other types of algorithms to create better designs, depending on the problem.
Okay. And maybe we have time for just a couple more questions. Let's see. Somebody is asking about slide 24. And the question is, in the measurement assessment slide, which is slide 24, how do you determine the true value?
Oh, that's a very good question, and it's something that's not always known. And so the accuracy part of a measurement system, you often see, will get almost no treatment whatsoever. They'll just assume that, well, there's no bias problem. We just move on, and we're more concerned about repeatability and reproducibility, the variation involved, which is often true. So it's got to be that you have either a golden standard. I like to call it a golden part, where you know exactly what that true value is supposed to be, and you measure. You take other parts that you have take them off the line, and you're going to compare them and see if has bias crept in, or do we have a problem with it. But the only way you know a true value is, which is very rare, is if you have been if you consider, we say that's what it is, and you have maybe a true part or a golden part to measure it against. Otherwise, we don't have that. And so the assessment, or accuracy assessment, is often less of a concern to people than precision. Right or wrong, that's what they tend to do. So that's why we don't see a lot of research done and new methods for that, although there is some out there. And they're trying more with, what if I don't have a true value and I have to estimate it from past or historical data. So we don't really often know that value.
Okay, thank you, Connie.
Mm-hmm.
Someone else is asking, they say that they've never seen the ratio of PPK and CPK be used. Mm-hmm. And they're asking for if you could just elaborate on that a little bit.
Sure. If you look at what this is helping you identify is if you have an unstable process over time. If you look at the two graphs at the bottom, if for example, C sub pk, the C sub pk values we often considered short-term, so we would use the short-term variation that you see in the figure at the bottom. We would use the short-term variation to calculate the C sub pk. We would use the value of the long-term variation for calculating P sub pk, for example. And what this is saying is, if you calculate that index, C over P, which if you look at the figures, if you look on the left-hand side, if you took that variation in long-term and it was divided, or excuse me, take the short-term variation divided by long-term variation, that index, that C over P, would be quite small. It would be less than 1, right? And on the right-hand side, the short-term and the long-term are basically equal to each other. So you have a situation there where if I use those in calculation of C and calculation of P, then my ratio should be around 1. So there are a couple of papers out there. There's a statistics roundtable paper in Quality Progress that I and Kevin White wrote on these types of indices that might give you more details than I can at this time. But it all has to do with looking at the long-term and short-term variation and comparing them, as you see there. Does that make sense?
Okay, I think so.
Well, yeah.
Hopefully it does. And a sort of follow-up question is, can the same ratio be applied for CP and PP?
Yes.
Okay. All right. And we have several other questions, but I think at this point, what I'll do is send those questions to the two of you, Connie and Christine, via email. And then you can just send those responses back to me, and I'll forward that information to the attendees so that the information can be shared to everyone. But thank you so much for taking the time to share this webinar with us, and to also open yourselves up for some discussion and making the slides as well as the paper on which the presentation was based available for the attendees.
Oh, it was our pleasure.
It was our pleasure. Thank you very much.
Yes.
Thanks, everyone, for attending.
Yeah, thank you.
Thank you to all of our attendees. Again, the recording of the webinar will be available on the division's YouTube channel, and that's youtube.com/ASQ we try to get it up there as quickly as possible, so hopefully by this evening or tomorrow. So be sure to share with colleagues and coworkers. So thank you again for presenting with us today. I hope everyone on the phone enjoyed the presentation. And our next webinar is expected to be the last week of April. Details on that will be announced soon on the division's LinkedIn group page, as well as our website and email newsletter. So be sure to mark your calendars for that one. Thanks again, Connie and Christine, and I hope everyone has a great day.
Thank you.
You too. Thank you so much.
Yep, bye-bye.
Bye.